Hi everyone, today we're going to talk about logarithmic functions. And just like we did with exponential, we're really just looking at this as a review, so I'm not going back to the beginning, but I will make sure that we talk about everything you need to know. So let's start with, when I say the word logarithm, how does it make you feel? Are you anxious, nervous, confused, sad? Let's try to change that. So let's start with the question, what is a logarithm? A logarithm is just the reverse of an exponential function. So what we're going to do is take any point xy that was on our exponent, and we're just going to flip it over to yx. Remember, we've talked about 2 to the x, and we have these values, -2, 1/4, -1, 1/2, 0, 1, 1, 2, and 2, 4, as points on our graph of 2 to the x. Now I'm just going to flip those around. So I'll have 1/4 -2, 1/2 -1, 1, 0, 2, 1, 4, 2. This then is the opposite, which we call the log base 2 of x. I'm going to graph those points on the same coordinate system so you can see what their graphs look like together. So I have 1/4 -2, 1/2 -1, 1, 0, 2, 1, and then 4, 2. This curves up along the y-axis and it goes over, picking up all the points. You can see a lot of things that are opposite. 2 to the x had a y-intercept. Log base 2 of x has an x-intercept. There was a horizontal asymptote for 2 to the x, and that was along the x-axis, so I have a vertical asymptote along the y-axis for my log. Both of the functions are increasing. You can see there is some symmetry. They look pretty similar, and if we wanted to, we could draw in this line y equals x, which is their symmetry. So if I fold along this dotted line, I should see the things line up pretty well. So let me remind you of the definition of a log. The log base b of y equals x means that b to the x equals y. I kind of think of it as this circular b to the power x is equal to y. That helps me out. A couple things we have to say about b. b is greater than 0 and not equal to 1. Well, that was the same thing we said when we did exponential functions. We also need to watch that y has to be greater than 0. This says you can only take the log of a positive number. So let's try a couple to make sure we really have that feeling. Let's say I had the log base b of x minus 9. Now putting in the log base b says it doesn't matter what the base is. So I could have log base 2, log base 3, log base 4, it doesn't matter. It could be anything. I have to have that x minus 9 is greater than 0, which means x is greater than 9. And we're going to write that as an interval, 9 to infinity. Notice this interval is open, so this is not greater than or equal to 9. This is completely bigger than 9. Let's try another one. I have g of x is the log base 7 of 10 minus 2x. Again, I'm not going to use that base of 7, so we're going to take that 10 minus 2x, set it greater than 0. That means negative 2x is greater than negative 10. Now remember, when you divide by a negative, you are going to flip the sign of the inequality. That means I have x is less than 5. Less than 5 means I'm starting from negative infinity. I'm going to 5, again, open on both sides. Let's try one more. h is the log of 2x plus 4. There's no base written at all. We'll talk about it in a minute, but I wanted you to say this is a common log. Remember, that's a log that has a base 10. I'll remind you in a little bit. We'll talk about that more. So we're just taking the 2x plus 4, setting it greater than 0. 2x is greater than negative 4, says x is greater than negative 2. So I go from negative 2 to infinity. Let's write some logs as exponents. We want to see the relationship between the log and the exponent and be able to work back and forth with it. So our definition says log base b of y equals x says b to the x equals y. So you look for the base of the log and that becomes the base of the exponent. So first one says log base 3 of x equals 2. The base of my log is 3. The base of my exponent will be 3. I'm raising 3 to the power 2. And that's going to give me x. Not trying to solve here, just trying to rewrite. The next one said log base b of x is 4. So base b means I have b to the 4th. So b raised to the 4th, that will give me x. Let's do the opposite. Let's write exponents as logs. We're still looking at that same definition that log base b of y equals x means b to the x is y, and we just want to kind of deconstruct it. 4 to the x equals 256. So when I make my log, the base of my log is the base of my exponent. And what I'm doing is saying the log of this number, 256, would be equal to x. So as you're kind of pulling it apart, you look for the 4, which was the base. Here's the base. The exponent goes on the other side of the equal sign. So this exponent came over, it's over on the right, and the 256 is what we're taking the log of. Same thing with e to the x is 17. So my base is e. Let's write the log base e. My exponent goes on the right side, and I'm taking the log of 17. Log base e is a special log called the natural log. We will talk about that more as well, but we'll go ahead and put it in there. So when I say log base e, we're not really going to write it that way. We're going to call it the natural log. So let's do a quick check, see how we're doing with understanding what logs are. But primarily what I want you thinking about is when you see log, I want you to think what power. What power of the base do I have? So I'm starting with 4. And I'm thinking, what power of 4 is 64? Now, you can grab your calculators and you can start doing powers on there. So you know 4 to the 1 is 4, 4 squared is 16, but if you put in 4 cubed, you get 64. So the power of 4 that gave me 64 was 3. Log base 5 of 25. I think, what power of 5 gives me 25? Well, I know 5 squared is 25, so that means this is 2. Log base 2 of 256 says you're putting your calculator a bunch of times trying to figure out what power of 2 is 56. So just start kind of pushing some buttons. Try like 2 to the 5th, 2 to the 6th, 2 to the 7th, 2 to the 8th, and finally 2 to the 8th gives you 256, so this is 8. And that's how I would do this. I'm not trying to do anything fancy here. I'm just doing powers of 2 until I get to the power that gave me 256. Let's look at log base 7 of 1 over 7. We have talked about this a bunch of times so far. We know what happens with exponents and fractions. It means, how did I get from 7 to 1 over 7? I used a negative, and it was just negative 1. Very similar then to look at the log base 7 of 1 over 49. I know 7 squared is 49, but because it's a fraction, that means I had a negative, so it's negative 2. At the log base 3 of 243, again, you start pushing buttons into your calculator. You know 3 squared is 9, 3 cubed is 27. You could try 3 to the 4th, it gives you 81. But if I do 3 to the 5th, you should see 243, so this is a 5. Log base 5 of 125, again, start pushing some buttons. You should get that that's 3. And then here I have a fraction. So that fraction tells me I'm going to have a negative answer. If I try 5 to the 4th, I get 625, so that tells me this is negative 4. Log base 8 of 1, this is going to be 0. Now look at the last one I have on this page, the log base 5 of negative 5. This is kind of a trick question. It doesn't exist, it's undefined, like I can't do that. I can't take the log of a negative number, so if you get a problem that says find the log of a negative, you say you're not going to get me, right? That's a trick, that I'm not going to fall for it, and you know there's no answer, it's undefined. So let's go back to talking about common logs. I mentioned earlier that the log base 10 of x is log x. So when you don't see a base indicated, it means it's supposed to be understood to be a 10. What's great about that is your calculator does have the common log on it. So if you're trying to do one where you're like, I want to put this in my calculator, here's your go-to. You can go to the calculator and do log base 10. What is it doing? It's doing powers of 10. Well, I just said that the log of 1 is always 0. This log of 10, so what power of 10 is 10? It's 1. What power of 10 is 100? 2. Then I have a log of 0.001. If you wanted, you could write that as 1 over 1,000. Like maybe that would help to see that relationship. And then you could say, well, definitely I know it's negative because it's a fraction. And then you can see there's 3 zeros, so that would be power negative 3. If you're like, nope, that's not going to happen, we could always go to the calculator, and let me show you 2 different calculators to make sure we understand what we're supposed to do. So how about I start with the TI calculator? You first want to locate where your log is. So on this particular calculator, it's over in the first column, and you can see log. On top of log, you can see 10 to the x, and that's kind of a nice indication that there's a relationship between the log and a 10, right? So I can see that 10 in there indicating what's going on here. So I'm going to hit log, and then let's put 1. That was our first one. When I push enter, it says 0. Let's try again. I had log of 10. We can see it's 1. I have log of 100. And notice every time I hit log, it pops a parenthesis. We need to make sure we're closing parentheses. We want to get used to that and have a really good habit of it. And this is the one we probably want to see the most, is log of 0.001, and it says negative 3. And just to show you, you could do the same thing. I popped over to Desmos, and in Desmos I could type log and then put 1. I can type in log of 100, log of 0.001, and it does the same calculations. If you could also open the keypad, go over to the functions, and under miscellaneous it has logs. So if you want to do logs using Desmos and you don't want to type it, use the miscellaneous under functions. Notice it also has a log base A. Notice it also has log base A, so if I hit log base A, I could put down 2, maybe put in 256 like we did earlier, and you can see it will do the calculation for you. You could also type log, hit the underscore 2, that makes it move down, and then type 256. So our second special log we need to talk about is natural log, and this is my preferred log, so you're going to find I'm going to use this a lot this semester. And the natural log is just the log base e of x. Again, we'll pop through a couple questions just so you understand what we're doing. So natural log of 1 is 0, because all logs of 1 are 0. Natural log of e says, what power of e do I have? Well, the natural log of e, this is e to the 1, so my power is 1. That's how I want you thinking. When I say log, you think power. So here, natural log of e cubed, well, what power? It was 3. Then we get to something like the natural log of 154. This is again where we go back to the calculator and see what does it say. Let's try the TI. Over here, here's natural log. Again, look at this relationship that's here. E to the x, natural log. Those two are on the same key together because they're related to each other. Now when I hit the natural log of 154, we are going to get a decimal, which means you're going to have to approximate the answer. So look for that prompt to say what you're going to round to. So let's do 4 decimal places. This is 5.03695. So the 0369 would be 4 decimal places, but that 5 says you really need to round up. So we're going to call it 5.0370. So we're going to say 5.0370. There's 4 decimal places. Let's try the same thing with the natural log of 34,891. So I have the natural log, 34,891. Again, I'm going to do 4 decimal places, so 10.4599 followed by an 8. So that 8 rounds the 9 up, which rounds the next 9 up, so we end up with 10.4600. Let's go through some properties of logs. Look at these as log base b, so it doesn't matter what base they are, they work for everything. The first one says log base b of b is 1. Remember the question is, what power of b do I have? I just have the first power. Log base b of 1 is 0. That says every log of 1 is always 0. The ones I think you use more are the log base b of b to the x is x. Look at, I have the log base b and I have b to the x. Now this is how we introduce logs, is saying the logs are the reverse of an exponent. When I put them side by side, think of them as canceling out. So you're saying, what is the power that I'm raising b to get b to the x? Well, obviously the power is x. Flip that around, write it the other way. I have b to the log base b of x. It's also x. Again, I'm seeing that exponent written with the log. They cancel each other out, and we come back to what we started with. Let's make that more particular and use it for natural logs, which again is how we're going to see it more in this class, because natural log is my go-to logarithm. So I have the natural log of e is 1, the natural log of 1 is 0, and then these two we use a lot. The natural log of e to the x is x, e to the natural log of x is x. Let's find a couple values. Keep in mind, e to the natural log of x is x. That's the property we want to use. So e to the natural log of 4 will just be 4. E to the natural log of 92 is 92. E to the natural log of x minus 7 is x minus 7. Flip it around. Now I'm using the natural log of e to the x is x. Natural log of e to the 5th is 5. Natural log of e to the negative 3 gives me negative 3. Natural log of e to the 3.5 is 3.5. Natural log of e to the x plus 3 is x plus 3. So again, we're seeing natural log and e, when they're together, cancel out. 3 more rules that we're going to use, and we're going to use them a lot all semester. The first one is the product rule. It says the log base b of m times n is equal to the log base b of m plus the log base b of n. So when I multiply, I add. This really comes from looking at exponents. When I have a to the m, times a to the n. So I have the same base. What do? I add the exponents. Let's use that rule. I have the log base 3 of 5 times x. This is being multiplied, so I can expand that and say that's the log base 3 of 5 plus the log base 3 of x. When you expand and you turn this into 2 logs, make sure you keep the base there so we know what we're doing. Let's expand again. Now I have the log base b of x, y, z. 3 things being multiplied, so we're going to call that the log base b of x plus the log base b of y plus the log base b of z. Quotient rule says the log base b of m over n is the log base b of m minus the log base b of n. Again, we are taking this from our rules for exponents. A to the m divided by a to the n, same base, I subtract m minus n as my exponent. So that we're seeing the same thing for the logs that we do for exponents. Again, let's practice. Log base 4 of 7 divided by x would be the log base 4 of 7 minus the log base 4 of x. The natural log of x plus 3 divided by x minus 2 is natural log of x plus 3, and I like to put the x plus 3 in parentheses so I know the natural log is of the whole expression, and then minus the natural log parentheses x minus 2. We also have the power rule. Power rule says the log base b of m to the p is p times the log base b of m. That's like our exponent, a to the m raised to a power p. We multiply the powers. The log base 3 of x to the 5th, we're going to bring that power 5 in front, and I have the log base 3 of x. The natural log of the square root of x, let's start by writing that again as the natural log of x to the 1/2 power. So I want to express it as a power. Then I can bring that power in front, and I have 1/2 the natural log of x. Let's combine the rules. The log of x squared times y to the 5th. I see a multiplication, which turns into addition. So I have the log of x squared plus the log of y to the 5th. I'm going to bring the power down. I have 2 log of x plus 5 log of y. The next one says log of 7x over y cubed. Important that you see this as 3 things, 7, x, and y, so 3 parts. So the top part is being multiplied. I want to turn that into the log of 7 plus the log of x. And then the y is in the bottom, so I'm going to subtract the log of y. And let's just go ahead and bring that 3 in front because it's a power. Here I have e to the x equals 5.21. But remember, we know that the natural log of e to the x is x. So let's try that. Let's take the natural log of e to the x, and that'll give me the natural log of 5.21. So the natural log of e to the x is x. If I want the exact answer, I would put 5.21. I could also give an approximate answer by putting the natural log of 5.21 in my calculator, and it gives me 1.650, and I'm going to round it to 6. Let's do another one. Solve e to the 2x is 45. Again, I'm thinking the natural log of e to the x is x, so I'm going to take the natural log of both sides. The natural log of e to the 2x equals the natural log of 45. So as long as I do the same thing to both sides, I haven't changed the value. The 2x comes down, so now I have 2x equals the natural log of 45. I need to divide by 2, so I have the natural log of 45 over 2. This again is the exact answer. I can also get an approximate by going into my calculator and putting the natural log of 45, close the parenthesis, and then divide by 2. This gives me 1.9033. Be careful with your calculator. Make sure you put the parentheses in, and you do not divide 45 by 2. That'll give you a completely different answer. Let me show you that. So watch, I have the natural log of 45, close the parenthesis, then divide by 2. There's our 1.9033. Versus if I do the natural log of 45 divided by 2, where I didn't close the parenthesis, so it did divide by 2, and it would be 22.5. It's bigger, it's 3.11. So watch for that. Make sure you're looking at notation, close your parenthesis. That'll help you from having to redo a problem because you made like a little mistake. A little bit bigger, I have 6e to the negative 0.15x minus 3 equals 2.95. We want to use the natural log of e to the x as x, but e has to be isolated, so I need e by itself before I can take the natural log. So I don't want to take the natural log yet. I want to move the 3 over. I have 6e to the negative 0.015x equals 3 with the 2.95 gives me 5.95. I'm going to divide by 6. I have e to the negative 0.015x equals 5.95 over 6. Now we can take the natural log. Natural log on the left, e to the negative 0.015x. I put a natural log on the right. And notice I don't grab my calculator and put 5.95 divided by 6. I'm just going to leave it alone, go to my calculator at one time. The natural log of e to the negative 0.015x is negative 0.015x. And on the right side, I have the natural log of 5.95 over 6. So my last step is to divide by the negative 0.015. So x will be equal to the natural log of 5.95 over 6 divided by negative 0.015. Okay, this again is exact. Exact doesn't mean much to us. We have no idea what number that is. So let's go ahead and put it in the calculator as well. It'll give us an approximate. So I have the natural log of 5.95 divided by 6, close the parenthesis, and then divide by negative 0.015. I got 0.55788. We're going to call that 0.5579. Well, what happens if I change it from e? What if I don't have an e to the x? How am I going to solve that? I'm going to use this natural log of m to the x is x times the natural log of m. Now, earlier I wrote it as p, but I thought it might help you see it better if I wrote an x in. So I'm still going to use natural log. Even though this is an e, I'm still going to use it because it'll bring the power down. And that's the hard part of these. The x, the variable I'm trying to solve for, is in the exponent, and I just need to pull that x down so I can solve for it. So I have the natural log of 3 to the x equals the natural log of 57. Okay. The x comes down. Now I can divide. I want to get x by itself. I'll have x is equal to the natural log of 57 over the natural log of 3. This is exact, but I can put in my calculator, and I get that this is about 3.6801. Very similar, I have 1.3 to the 4x equals 52,000. I'm going to start by taking the natural log. The 4x comes down. I have 4x natural log of 1.3 is the natural log of 52,000. Now I want to divide. I'm trying to get x by itself. So x by itself means I need to divide by 4 and by 1.3. X is going to be equal to the natural log of 52,000 over 4 natural log of 1.3. This is one I think I should show you twice, so I'm going to show you in Desmos and also in the TI. Starting with Desmos, I can put in the natural log of 52,000 divided by. Now watch the divided by goes into the denominator, and then I can type 4 natural log of 1.3. And I get my answer 10.34725, so we're going to call it 10.3473. Compare that to if I put it into the TI calculator. I put in the natural log, 52,000, close parenthesis, divided by 4 natural log of 1.3, and we're not going to get the same answer. See, I got this small 0.7122. The problem is, in the TI, I need to put parentheses around the 4 times the natural log of 1.3. Try again. Natural log 52,000. Close those parentheses, divide by parenthesis 4 natural log of 1.3. And now we're going to get the same value. We got the 10.34725. It's all about order of operation. So in Desmos, I could see clearly the separation from the numerator to denominator, and you can't see the same thing in the TI. So in the TI, if you have two things in the denominator, throw parentheses around it, and that'll save you from getting it wrong. Let's try a word problem. How long will it take $4,000 to double if it is invested in an account earning 3.5% interest compounded monthly? So I put back on the screen our formula, A equals P times 1 plus R over N to the NT, which is our compound interest formula. And let's label what we have. 4,000 is our P. We want it to double, which will be our A. So we have to think about how much is that. 3.5%, that's going to be our R. Compounded monthly, that's our N. We're solving for time. So A, the double, is 8,000. We started with 4,000. We have 1 plus 0.035. Monthly was 12 to the 12t. Now we're solving for t, which means I want to bring back in natural log. A lot of times I say these problems are kind of like divide, log, divide. So I'm going to start by dividing. I don't want to take the log until I isolate that exponential part. So I bring the 4,000 over, that gives me 2. That shows me that double. 1 plus 0.035 over 12 to the 12t. Now I can take the natural log of both sides. So the natural log of 2 is the natural log of 1 plus 0.035 over 12 to the 12t. The natural log is going to bring this 12t down. I have the natural log of 2 equals 12t natural log of 1 plus 0.035 over 12. So just like last time, I have these two pieces. I have the 12 and I have the natural log that I need to divide by. So I'm going to have the natural log of 2 over, let's put parentheses, 12 natural log of 1 plus 0.035 over 12, and this is going to give me t. So I have natural log of 2, close parenthesis, divide by, a parenthesis for the denominator, 12, natural log of 1 plus 0.035 divided by 12, and then I can close the parentheses, and I have 2. I have 1 for the natural log, and then I have 1 for the denominator. I push enter, and it says 19.833. For this one, I'm just going to write t is about 19.8, and I'm going to put years just so we remember what we were doing. All right, now we've reviewed our logs. We're ready to start doing derivatives with them.